Now we'll look at the mechanism number 2, the electrophilic addition that converts alkenes to haloalkanes. Here is a propene and HBr. The carbon-carbon double bond in the propene contains a pi bond over here and a sigma bond. And the electrons in the pi bond are more loosely held than the electrons in the sigma bond. Therefore, the pi region will act as a nucleophile that can donate electrons. In the HBr molecule, the H atom is partially positive, while the bromine atom is partially negative due to the difference in electronegativity. The bromine atom is more electronegative than the hydrogen. So consequently, the hydrogen atom will act as an electrophilic site that have a positive charge and can attract electrons. So now the two electrons in the pi bond attack the partially positive H atom, and the pi bond is broken down in this process. While in the HBr molecule, there is also a sigma bond over here. The two electrons in the sigma bond will be pushed towards the more electronegative bromine atom to form a bromine ion. And due to the attack of the electrons in the pi bond of the propene on the H atom, a new sigma bond is formed between the H atom and the carbon atom in the propenes that is originally connected to the double bond in the propene to form a 2' carbon cation. According to the Markovnikov rule, the H atom from the HBr will be preferably connected to the carbon atom, which already have more hydrogen atom. You can see over here there is 2 hydrogen atom, and here is only 1 hydrogen atom. So it will be connected to the one with more hydrogen atom to form a more stable carbocation, that is the 2'. Try to imagine if now we connect the hydrogen to another carbon. The positive charge will be located on this one is the primary carbon. So 1' carbon cation will be formed. This is not preferable because the 2' carbon cation is more stable than the 1' carbon cation. So the hydrogen atom will be always attached to the carbon atom in the double bond with more hydrogen atom, according to the Markovnikov rule. So now it comes to the second step, the rapid reaction. There's something to add on. For the first step, for the formation of carbon cation and halide ion, you can see a word of slow on the reaction arrow. So what does it mean? It means that this step is a slow process because the activation energy for breaking the pi bonds over here and initiating this reaction is relatively high, making the first step is relatively slower than the subsequent step. So now we come to the step 2, the rapid reaction with the bromide anion of the 2' cation with the bromide ion. So now the bromide ions act as a nucleophile and attack the 2' carbon cation to form a new sigma bond here. And you can see a word here, the fast, this is a fast reaction because the 2' carbon cation is stable, it's more stable than the 1' one, And the second reason is the bromide ion nucleophile can readily attack the electrophile 2' carbon cation. The last reason is after the slow reaction above, the energy barrier becomes lower. So this is the reason why the second step here is a fast reaction. That's all. Two bromopropane is formed.